Could you give me this remote? Yes. Thank you.
Welcome back, everyone. Our second speaker, who I have the pleasure to introduce again, is Reynold that will tell us about the Dani correspondence.
Thank you. Okay, so this is my final lecture. I just want to quickly go through what we saw last time. So we introduced a quotient of our group G, PSL to R, by a discrete subgroup, PSL to Z. And we also showed that gamma, PSL, from now on I will use this notation. So G will be always PSL to R and gamma PSL to Z. We show that gamma is a lattice in the sense that it admits a finite volume fundamental domain. We introduced a distance, dx, defined in the following way. So dx, the distance between gamma G1 and gamma G2 is this inf. And we also introduced the right invariant measure mx on x, defined by using any fundamental domain, taking the projection of a set, and then using the measure on the unit tangent bundle in the hyperbolic plane to compute the area of this set. And this is well defined. Okay, so we also have a flow on this set. So again, x is G mod gamma. I take the geodesic flow in the unit tangent bundle, I push it down to x. So I define gt of gamma g as gamma g times the matrix AT, where AT is this nice diagonal matrix. I also introduced the visual map, which essentially, which goes from the unit tangent bundle to the real line, so the boundary of the hyperbolic plane, and takes an element, so a point and a direction. It follows the unique geodesic exiting z in that direction, and it takes the point where it hits the real line. Okay, and the correspondence that I want to prove today, so today's goal is to prove this, is that the hitting point, so the image of the visual map to the power -1, so the inverse of this real number, is badly approximable or singular if and only if the geodesic flow applied to this set is bounded in x. Okay, so x, again, you can see x as this set here, and you will see an orbit associated to the point ZV, okay? And this orbit is bounded, meaning that it stays below a certain line in this window that you see, if and only if this hitting point inverse is badly approximate, okay? Good, so I want to start by introducing the last character of this tale in a way, which is the moduli space of lattices. So,
I'm sorry, what if the geodesic is a vertical line?
Yeah, so if the geodesic is the vertical line, the point is 0.
Okay.
Okay? And clearly 0 is not badly...
So it's always in this case...
So it's clearly not badly approximable,
Okay.
and you have that the line diverges. It just goes to infinity, right? That's clear. And it's also singular. 0 is singular, being a rational point.
So when you say diverges, what's the precise sense that diverges?
It means that it leaves every... So remember, the the topology that you have on this set here, on this window, is the topology induced by this distance here, which is also the same as the Euclidean topology. Okay, so leaves every compact set. It means that so the only way that you have to escape to infinity is to go to go here, right? And diverges means that it's not allowed to come back.
It doesn't come back.
Okay, so it means that if I give you a certain compact set, you can give me a time such that after that time you never go back to that compact set. Okay?
If it's recurrent, so if it's neither bounded nor it goes to infinity.
Okay, then it's, I mean, singular union badly approximable is not the whole line, right? So there are many, many other behaviors that one thing can exhibit, and you can make this correspondence more precise. But this is not the goal of today's lecture, okay? So we wanna check somehow the opposite ends of the spectrum, right? So divergent and bounded, okay? Good. Okay, so right, so let me give the following definition. So definition, a lattice in R2. So for now I'm going to work in R2, but you can do the same thing in RD. Whatever dimension is a discrete Z subgroup of full rank. Okay, so maybe you don't even need to specify this, but so it's something of the following shape. Lambda is equal to A V1 plus B V2, such that A and B lie in Z, and V1 and V2 lie in R and are linearly independent. Okay? So it's some kind of grid, right? If you want to picture it, right? So you have, I don't know, two vectors, one like this, and you have a grid like this. Okay, so this is your V1 and this is your V2, and this is essentially a special case of the definition of lattice that we gave last time. Okay, but for the specific group. R2. Okay? Good. So then one can define the co-volume of a lattice. So the co-volume of lambda is the volume of the parallelepiped, or area. In this case, let's say area. Area of the parallelepiped parallelogram in reality. Okay, spanned, so defined by a basis. So for example, in this case, I have these two linear independent vectors, and as a co-volume of lambda, I take this, the area of this parallelogram. Okay, and why? So this is well defined. So well defined because you can always write lambda as A Z2, where A is some matrix in SL2R, okay? And the only way you can choose a different basis is by multiplying A by a matrix in SL2Z. Okay, so change of basis, change of basis corresponds to right multiplication. I think, or right multiplication by a matrix in SL2Z. Okay, but of course this doesn't change the volume, right? Because if you multiply A by, so if you just take a change of basis, this is the determinant of A, and you multiply A by a matrix of determinant 1. So this is clearly well defined. And okay, so now let me define L2 as the set of lambda contained in our 2 lattice, such that the co-volume of lambda is equal to 1. Okay? Good. So, alright, my goal now is to see this space. I want to see this space as SL2R mod SL2Z. Okay? So if you look at this formula, this is essentially true, but not quite, because in reality here the stabilizer of the lattice is right multiplication by a matrix in SL2Z, right? So what you want to do is you want to see lattices in a different way so that this space of lattices can be identified by this quotient, where instead of quotienting by the right action of SL2Z, I quotient by the left action of SL2Z, right? So if you look, you all agree with me that a lattice can be written like this? Right? Everyone agrees, right? Okay, so here to get a different basis, I have to multiply on the right. But in my space, the original space I had, right, I want a quotient by the action of SL2Z on the left. So I have to see lattices in a different way, right? But in reality, it's very easy to see that lattices can also be written as lambda equals Z2 transpose times a different matrix, say A prime. Okay, so you take a matrix A, B, C, D, and then you have PQ here, and this again defines a lattice. Okay, but now your lattice will be something of the form PAB plus QBCD. Okay, so it's just a different way of writing lattices. So this is the usual way, but one can also do it in this way. And if you do it in this way, then you can see L2. So this allows you to identify L2 with the quotient SL2R modulus the left multiplication action of SL2Z. Okay? And because clearly the stabilizer of a lattice will just be multiplication on the right by a matrix in SL2Z. Is this clear for everyone? Okay. Good. Okay, so then this means that we have remark. One also has that SL2R modulo SL2Z is the same as PSL2R mod PSL2Z. Because remember, PSL2R is just SL2R quotient out by the multiplication action by plus or minus the identity, but this is also a matrix here. So it just disappears when I take it. Right? So these two quotients are exactly the same thing. Okay? So this implies that we have a long chain of identifications. So this gives us the long chain of identifications. So T1H, the hyperbolic and the unit tangent bundle of the hyperbolic plane, identified with PSL2R mod PSL2Z, which is also identified with SL2R mod to the left SL2Z, which is also the moduli space of lattices in dimension 2. Okay, good. But now, okay, this identification here is easy, and I don't want to I don't want to spend too much time. So here we have an identification through action on the element II, and we know that this is a diffeomorphism. Okay, so what about this side here? What kind of identification is this? So L2 for now, as I have defined it, doesn't really have a structure. Okay, so before going on, I want to quickly define some kind of structure, at least I don't know, a topology on L2. Okay. Let's see. So let me erase this. I think I erased the wrong part, but okay, so topology on, feel free to interrupt if you have questions. So topology on L2 is defined in the following sense. So you have that, so to define a topology I can just define a way of saying when a sequence of lattices converges to a lattice. Okay? So if I take lambda n, I say that lambda n converges to lambda if and only if there exists a basis, so a sequence Vn Wn of Z bases of lambda n such that Vn Wn converges to Vw and Vw is a basis of lambda. Okay? So exercise that this is well defined. Okay? So this gives you a topology on the space Ln, in which sense, through convergence, you can identify all closed sets. Okay, so you say a set is closed if and only if whatever sequence you take, a converging sequence you take in the set, it goes to an element in the set. And now, remark, so L2, with this topology, is homeomorphic to our space X equals G mod gamma. And why is this? Well, you just have to remember what was the distance that we defined on the space X. Okay, so the distance was dx gamma G1, gamma G2. So now you're allowed to see these as lattices. So G1 is just a matrix, so basis vectors, right? V1, V2. And here you have SL2Z. So this is the inf for gamma in gamma of the distance in G of gamma G1, gamma 1 G1, gamma 2 G2. Okay, so sorry, here it's gamma 1, gamma 2, and gamma. Okay, so essentially what you're doing is that you're taking the distance between two different bases of these two lattices. Okay, because you're essentially saying, okay, so this gives me a lattice, this gives me a lattice in R2. Okay, I run through all possible bases of the lattices and I check which ones are closer. Okay, and this clearly agrees with the definition of convergence that we gave. Right? So the topology that I have introduced here and the topology that I have here are the same thing. So saying that something is bounded or compact in the set T1H, or that something goes to infinity in the set T1H is the same as saying this in the set L2 because I have a homeomorphism. Okay? Good. Okay, so now I want to good. Yeah, right, so we said that this is a homeomorphism, and we also saw that the space SL2R mod SL2Z is not compact, right? And the way you diverge to infinity is by going up like this, right? So what's a way of going to infinity? So since this space is not compact, by this remark, also the space L2 must not be compact, right? And what's a way of diverging in L2? So let's say remark L2 is also not compact. And for example, take the sequence of bases. So take lambda n, the lattice generated by 1 over n e1 and n e2. Okay, so what's this lattice? This is just a lattice that has is generated by a really long vector here. Oh, sorry. Yes, no, this is correct. Right, so a really long vector here and a really short vector here. So now the volume of this, or the area of this rectangle is 1, right? But you can extract no convergent subsequence from this sequence of bases, right? Because, so no convergent, in R2, okay? In R2, convergent subsequence of bases. Pardon? No. So in L2 the topology is defined as take a sequence of bases, look where it goes in R2. Okay? So yes, I'm sorry. So in the sense that in R2 it has, so any sequence, any subsequence of this thing. I'm sorry. No. It's true. Also in R2 it has no convergent subsequences, right? Because whatever subsequence you take, this goes to infinity, right? So even in R2 this has no convergent subsequences, right? But it's still a sequence of elements in the space of lattices. Okay. Good. Okay, so and now to prove our main theorem, we need a way to understand when a set in our space of lattices or in T1H. So I kind of showed it to you on the picture, but now I want a systematic way of saying when a set is compact. Okay, to prove this the statement, right? Because the statement includes some remarks about compactness, right? So some compactness property, right? So, and for this, I want to use the Mahler compactness criterion, which says the following. So, theorem, omega contained in L2 is compact if and only if there exists a lower bound delta positive such that for all v in lambda, or for all lambda in omega, and for all v in lambda, you have that the length of v is bigger than delta. Okay, so this you can also write as delta 1 of lambda being larger than delta. where delta 1 is by definition the minimum for v in lambda of the length of v. Okay, so I give this as a definition. I call this the first minimum. Yes?
Maybe we also want it to be a closed set? Or instead of compact,
Yes.
compact.
Yes. Thank you. Okay, good. So how to prove this? So to prove this, we need an intermediate result. I'm going to just give an idea of how to prove this. I don't have too much time. So first we need the following theorem. So Minkowski's first theorem that says the following. So for all lambda in L2, there exists v in lambda intersect -1, 1 to the power 2. Okay, so for any lattice that you pick of covolume 1, there will always be a vector that lies in this square of side length of edges of length 2. Okay, and okay, so the proof of this is also quite easy, but for now I want to skip it. Okay, so it's not complicated. Good. So using this, let's now prove Mahler's compactness criterion. So proof of Mahler compactness criterion. Okay, so right. So suppose that omega is not compact, right? If omega is not compact, then or is unbounded, then there exists. So there exists a sequence of lattices in omega such that lambda n is generated over z by Vn Wn and Vn tends to 0. Okay, so the only way that you cannot the only way you're unbounded is that if one vector becomes extremely long and the other vector becomes extremely short. Okay? And by this, you have that this sequence admits no convergent subsequences, as we have seen already. Okay, so on the other hand, suppose that, so is this clear? Do you have any questions about this? Okay, good. On the other hand, suppose that this happens, right? So by Minkowski's first theorem, there is a first. Let's fix first a lattice lambda in omega. So let's fix lambda in omega. So by Minkowski first theorem, there exists v in lambda such that the norm, the infinity norm, so max v1, v2 in modulus is less than 1. Okay? So a vector lying in this square. Good. So okay. Good. So now pick W and assume V primitive. By primitive, I mean V is different from lambda, let's say U with U in lambda. Okay, so it's not a multiple or of another vector. Okay, so I fix a lattice in ohmic. There exists a vector here. I take the shortest possible vector on this line. Okay, so say I can take the shortest possible vector, so I can assume it primitive. Okay, and so exercise D can be completed to a basis VW of lambda. Okay? So this is something you can always do. And it's a really it's not a complicated statement, but I don't want to prove it now. Okay, so and now let's look at what happens, right? So suppose that here we have our vector v, right? And let's call this w, and suppose that this is the line rv. Okay, then so here we have our vector v, right? So we know that the area, the covolume of lambda is equal to 1, and we also know that the length of v is larger than delta by hypothesis. Okay, so we know that this area here is 1. This means that the distance between W and the line RV is less than 1 over delta. Okay, otherwise you would have that the covolume is larger than 1. Right, so if this length here is bigger than delta, this height must be less than 1 over delta. Otherwise, whenever you multiply together, you get something of area larger than 1. Does it make sense? No? Yes? Okay, good. Okay, so then if this is true, let's see. Yes, okay. Right. Okay, so this means that there exists lambda in R such that the distance between W and lambda V is less than 1 over delta. Okay, less or equal to 1 over delta. Okay, and then take yes. So this also implies that the distance between W and the integral part of lambda V is less than 1 plus 1 over delta. Okay, because I know that the length of V is at most 1, and when I go from here to here, I'm making a mistake of at most 1. Okay? Sounds good? Right. And then, just take as a basis of lambda, take V and W minus lower floor lambda v. Okay? Then what do you have? That then the norm, the infinity norm of, let's call this w prime, okay? You have that the infinity norm of v and w prime is between delta and 1 plus 1 over delta.
Should it be the over the length of v on the left-hand side instead of delta?
Sorry? The length of v is at most 1.
Okay, yeah, no, sorry. Yeah.
So, okay, so you know, you have that the distance
It
between,
was stupid, I'm sorry.
yeah, so, no. So you have that the distance between w and this vector here it's at most 1 plus 1 divided by delta. So if you subtract from this, you subtract this, you get something of length at most 1 plus 1 over delta. So the length of this second vector here is at most 1 plus 1 over delta. And the length of v, we chose v to be inside this square. Right? So, inside the square. So both the length of these vectors are less than 1 plus 1 over delta. Okay? So this means that, so every lattice in omega admits a basis VW such that the length of V and the length of W are between delta and 1 plus 1 over delta. Okay? And now, so this means that your bases essentially are stuck, your lattices all have bases that are stuck in some big annulus. Okay? So you have a smaller circle here, a bigger circle here, and your lattices all have bases here. Okay? So this means by compactness of this annulus that you can always extract a convergent sequence of bases. Okay? So I can extract a convergent sequence of bases. Whoops. Does it make sense? Okay, good. So this is the perfect weapon to address our to finish our proof. Okay? And so now we are completely ready. I hope, yes, I have 20 minutes. So in these 20 minutes, I will give you the proof of the correspondence by using Maller's compactness criterion. If I have time, I will go back to this, but this is just a 2-line proof. Okay? So for now, let's, if for you this was too quick, ignore it. Just think about this. Okay? So think about this. So you have this space of lattices, which is the space of all grids in R2. Okay? You have a topology in this space, which is a sequence of lattices converges to another sequence if a sequence of bases converges to the sequence, to a basis of the limit lattice. And a way to understand if a subset in this space is compact is to look at the shortest vector of the lattice. Okay? Good. So using this, let me prove the correspondence. Good. Okay, so let's start with let's see, ZV and T1H. Okay, so then by how I define my correspondence, I have that ZV is uniquely associated to an element G and G is of the form A, B, C. Okay? So the visual map, of ZV is what? ZV is what? So limit for t tending to infinity of GT ZV, which is also the limit for t tending to infinity of A, B, C, D, e to the plus t halves, e to the minus t halves, I. Okay? Good. And let's see, so now let me distinguish two cases. So one is the case where A is different from 0, and 2 is the case where A is equal to 0. Okay? So in the second case, exercise, omega z v is, let's see what's the case. A is equal to 0. Yes, omega zv is equal to 0. Okay, so this case here is somehow not important. We're not really concerned about this case here. Okay, so let's look at this case number 1, which is the most important. Okay, so and let's write out this. So what do we have here?
In
So
this case, sorry, when your visual map is 0, the omega is the visual map, correct?
Yes, so maybe I wrote it wrong. Yes, I made a mistake. What I meant here is the visual map is infinity. So your vector is pointing like this. Okay? So
The inverse is infinity.
no, the inverse is 0. I made a mistake here. So the visual map, in this case, we will now do the computation in this case, and you will immediately see how this follows from the first
Okay.
case. Okay, so but just keep this aside. This case is not important. This is what I want you to kind of see. Okay, so let's do this case. Right? So let's do exactly what Davide did last time. If A is different from 0, so remark, I have that A, B, C, D can be written as 1, 0, 1, X, A prime, B prime, D prime, 0. Okay? Why? Because then, so the product of this is just what? A prime, B prime, A prime, X, and B prime X plus D prime. Okay? So, and I can write every matrix such that A is different from 0 in this way here. Okay? So, in this case I cannot do it, because if this element is 0, then the second element is bound to be 0. Okay, but if the first element is non-zero, I can always do this. Okay, so in the second case, again, this case is kind of not important for the proof of this theorem, but I leave it as an exercise. Okay, so by writing our matrix like this, let's compute the visual map. So this is what Davide did last time, right? So we have that omega zv is the limit for t tending to infinity of what? So 1x 0, 1. Here we write a prime, b prime, b prime, 0, and then multiplication by e to the t halves, e to the minus t halves, and acting on I, right? And let's see, so what did I do? Okay, no, this is just a direct computation, right? So what's this? So this is just the limit for t tending to infinity of, so if you take the multiplication, right? So a prime, b prime, x, a prime, b prime. You also have, let's see, here you have multiplication by e to the t halves. Maybe let's write it a bit better. Okay, so this multiplies the first column. This also multiplies the first column. Here you have b prime e to the minus t halves, and here you have d prime e to the minus t halves. I hope this is correct, right? Yes. Okay. And so what's this? This
You
is
have x plus d prime, right?
yes. Sorry. Here I should have b prime x plus d prime. Okay, so this is the limit for t tending to infinity. Let's use the definition of our action, right? Of let's see. So it's a prime e to the t halves I plus b prime e to the minus t halves divided by x. So we just need to compute what the component z does. We don't care about the component b, right? So this is x a prime e to the t halves I plus b prime x plus d prime e to the minus t halves. Okay, and now these two disappear, and when you take t to infinity, what you obtain is 1 over x. Okay, so here in this bit here, I'm ignoring the v component. I'm just following what the z does. Okay, does it make sense? Okay, good. So I have 1 over x, so this implies that omega z v to the minus 1 is equal to x. Okay, so by using the same computation, you can address the second case, a equals to 0. Okay, so if a is equal to 0, what you have that this term is not here and everything goes to 0. Okay, so everything goes to 0, so what I wrote initially was correct. Okay, but the cases 0 and infinity are really not important for this correspondence. Okay, so good. Okay, so now we have to look at the orbit of this element through the geodesic flow, right? But inside our space X, right? So now we have to look at, so on the other hand, sorry, my chalk is a bit too short. Okay, so on the other hand, we have to look at GT, our matrix, so 1, 0, x, 1, a prime, b prime, b prime, e to the t halves, e to the minus t halves in G mod gamma, right? So one side of the correspondence is the visual map, and we've computed this number that we're interested in, and so the other side of the correspondence is the behavior of this orbit inside G mod gamma. Okay, and exactly. So here we do what Okay, so this is also equal to gt gamma 1, 0, x 1, a prime, b prime, 0, b prime. Okay? Good. So let's look at this orbit. Good. So since my orbit looks like this, what I want to do is I want to take this element on this side here and essentially say that this matrix here counts nothing. Okay, so I observe that gamma 1, 0, x 1, a prime, b prime, 0, d prime, e to the t halves, e to the minus t halves is also equal to gamma 1, 0, x 1, e to the t halves, e to the minus t halves, and then here I have, so I brought this on the other side, so what's left here is the conjugation of this by this matrix here, right? And okay, this is just a computation, this is a prime, e to the minus t, b prime, and d prime. Okay, so I just conjugated this. And now, okay, so this is an element that lives here. Okay, and I observe that in T, this element here is a bounded matrix, right? So it stays in some fixed compact set of matrices, and this means that this element here escapes to infinity or stays in a compact set if and only if, this whole element, if and only if this element stays in a compact set or escape to infinity. Right? So remark, let's call this element here, okay, let's not give it a name. So gamma 1, 0, x1, at stays in a compact set. Or escapes to infinity if and only if the element, so the initial element, gamma 1, 0, x1, a prime, b prime, d prime, 0, e to the t halves, e to the minus t halves, does the same. So to see this, you just have to use the fact that the distance that you define, so that on your space you have a distance. A distance is a continued function, right? So if you have that, say, this element stays in a fixed compact set, right? When you multiply by matrices in another compact set, right, the distance admits a maximum, right? So if these stay, say, in a big ball, then these also have to stay in a big ball. And if these guys go far away, since the distance is a continuous function, then these also have to go far away. Does it make sense? Okay, so then we've come to the conclusion that in reality, whenever I write a matrix through this decomposition, whatever counts is only the element x in this correspondence. So I have omega zv is 1 over x, and the limit behavior of my orbit is only dictated by this the limit behavior of this element here. Okay? Good. So, and essentially this allows me to conclude, because now saying what this, and now I apply Mahler's compactness criterion to this, and this gives me the whole correspondence. Right? So So for now, I'm considering bad approximability, right? So for now, let's do. So for now, let's focus on 1 over x in bad. Okay, so I'm sorry, not 1 over x, for x. Okay, so the inverse. So the singular case you can do by yourselves. For now, I just want to prove the badly approximable case, right? And good. So so again, the correspondence says that x is badly approximable if and only if this thing here stays in a fixed compact set, right? But now if I see this as a lattice, I can apply Mahler's compactness criterion, right? So then, let's see, gamma 1, 0, x 1, at stays in a fixed compact set if and only if, by Mahler's compactness criterion, there exists delta positive such that the maximum between what? So I have to take a basis vector, right? So what are my basis vectors? So if you look at the representation that we had before, this is a lattice of the form PQ 1, 0, x 1 e to the t halves e to the minus t halves. So as basis vectors, I can take, so as basis vectors, this gives vectors of the form e to the t halves p plus qx and e to the minus t halves q. Okay? So these are the elements, or maybe not even as basis vectors, but as lattice vectors. Okay, so lattice vectors, such that P and Q lie in Z. Okay, so, and by using Mahler's compactness criterion, this stays in a compact set if and only if the max of e to the minus t halves P plus qx and plus t halves and e to the minus t halves q is larger than delta. Okay? And now I claim that this claim star is true if and only if x is badly approximable. I'm already a bit over time. I'm essentially done. It's no joke. Okay, so one direction is okay, so let's see. Q times qx. Sorry. And this has to be true for all t positive. Okay? And so if this is true for all t positive, right? What do you have? You have that okay, maybe I'm a bit over time. Let's see. So okay. T halves q. Yes. So pick t. So to do this direction, okay. So pick t such that such that e to the minus t halves, so fix q, and pick t such that e to the minus t halves q is approximately delta halves, right? So this implies that the maximum is given by the other vector, so e to the t halves p plus xq has to be larger than delta for all p, and this implies that the product q times qx plus p is larger than delta squared halves, okay? And the other direction is trivial. Okay, the other direction is trivial because you know that q times qx plus p is always larger than a constant c, okay? And then you take some fixed t. From this you have that e to the minus t halves q, e to the t halves qx plus p is larger than c, and so the maximum also has to be larger than c. Okay, so this proves the equivalence. Does it make sense? And I'm so sorry for going over time. I just want to make a last comment. Why is this useful? So, because you can prove that this flow here, the action of this flow, or actually every element of the flow is an ergodic transformation. Sorry, the measure that we define on the space is ergodic with respect to every element in this group. This is a theorem by Hopf, right? And this tells you immediately that you can do this as an exercise, that the measure of badly approximable points is 0. Okay, why is this? Because if you had a non-zero measure of badly approximable x, you can multiply by whatever matrix you like here, right? This gives you a full measure set, so not a full measure set, a positive measure set of matrices that are that have an x that is badly approximable, right? And this would give you, by this correspondence, a positive set of matrices that whose orbit stays in a compact set. Okay? But this is impossible by ergodicity. So, for example, I didn't have time to say this, but an immediate application of this is that since the geodesic flow is ergodic, or each transformation in the geodesic flow is ergodic, badly approximable numbers have measure 0. Okay, sorry for going over time.
Any question?
Yes?
So this visual map, the omega,
Yes.
it runs always like, it does not touch the interval 0, 1.
What do you mean it does not?
You say the limit, it goes always to 1 over x.
No, but x can be any number. X, sorry? X can be any real number.
X is A over C.
Sorry?
X is A over C.
Yeah, x is A over C.
Yeah.
X is A over C and it can be any real number. So A, B, C, D is allowed to be any matrix.
Okay.
Okay, but the x component. So, and what you do, actually what you do in higher dimension is you forget about this correspondence with the unit tangent bundle and you only focus on space of lattices and this, and the group G mod gamma. Okay, because you don't have a correspondence with the unit tangent bundle of the hyperbolic plane. So you only use this. And essentially, well, factually, what you do is a larger version of this matrix. So you can do the same thing for vectors. Instead of x being a number, you can take x a vector, and you have exactly the same correspondence in higher dimension. But this is a baby case, and somehow I thought it would be more instructive for you to see the baby case instead of going over some vector computations. So yeah, okay. Hopefully. At least some of this stays with you. Yes?
Are there any like similar results if you consider not PSL to Z but some other function group with lattice and like what was can be?
So this I don't know if it has an application to number theory because to Diophantine approximation, because Diophantine approximation is directly linked to the space of lattices in R2, and the space of lattices is, the stabilizer of a lattice is PSL2Z. If you pick a different Fuchsian group, I don't know what's the meaning of that in terms of lattices. So I don't know if there are any other applications that go beyond the Diophantine approximation. Probably other people in the audience know better. And yes. And a comment, so all of this was formalized by Dani in around 1985, but the correspondence with lattices was already noticed by Davenport and Schmidt much earlier, and also a link with continued fractions was also known by Artin, I think. So it's an old mechanism somehow. It goes back, but now we call it Dani correspondence because he really formalized it. Okay.
Any more questions? Okay. No, let's thank our speaker again.
Actually, I do have one.